And I'll move to presenting the second paper. So it's by, the title is Injecting Domain Knowledge in Neural Networks, a Controlled Experiment on a Constraint Problem. And the speaker is Mattia Silvestri. So can you present the video, please?
Should have uploaded the pre-recorded presentation on.
Good morning, everyone. My name is Mattia Silvestri. I'm a PhD student from the University of Bologna. Today, I will present you our work, Injecting Domain Knowledge in Neural Networks, a control experiment on a constraint problem. Recently, deep neural networks have been successfully applied to solve constraint satisfaction problems, but they still are not close to the state-of-the-art approaches. At the same time, they may have some advantages. For example, when implicit soft or hard constraints are present, or for problems with well-defined sources of symbolic knowledge, which cannot be easily exploited during the search. For example, simulators or NPR propagators. In this work, we will focus on the second scenario. We performed a control experiment using a classical constraint problem as a case study, and assuming to have implicit knowledge derived from data and explicit symbolic knowledge that can be accessed prior to the search, but not during the search. The empirical knowledge is represented by the available solution, whereas the domain knowledge are the problem constraint. We start from a problem-agnostic deep neural network, and then we measure the effect of adding domain and empirical knowledge. As a byproduct of our analysis, we develop a general method to turn constraints propagated into information sources and distill them in the weight of the neural network. We also develop a method to obtain many training examples from a few solutions. We employ the partial Latin square completion problem, and using a classical constraint problem as a case study grants access to domain knowledge and makes easy the generation of the empirical data. All the constraints are well known, but we can selectively choose which can or cannot be employed during the search. In this way, we can perform a set of control experiments that would have been impossible in a real-world problem. We start from an existing work which proposes a data-driven and problem-agnostic approach in which a deep neural network is trained to extend a partial solution by making a single global feasible assignment. The input of the neural network is the one-hot encoding of the partial Latin square, and the output has the same encoding, but we require it to be continuous, because for each assignment we want a probability for each to be chosen as the next one. A training example is a pair of a partial assignment and a possible completion among all the viable ones. To generate the training set, we apply a random deconstruction procedure which starts from a complete solution and randomly choose one of the cells and assign the value, and then uses the resulting partial Latin square and the unassigned value respectively as the input and the output for the neural network. This procedure is performed iteratively until we reach an empty square. This allows to decouple the number of examples from the number of solutions. In fact, in some of the experiments, we perform the deconstruction procedure only once for each solution, whereas for other experiments, we perform the deconstruction procedure multiple times for each solution. We train a network in a supervised fashion, using as a loss function the categorical cross entropy between the output of the neural network and the target value. The knowledge injection is performed running a constraint propagator and treating its output as a multivariate function, which associates value 1 to assignment that have not been marked as unfeasible, 0 otherwise. Then we formulate 3 different approaches to augment the loss function with a regularization term which is inspired by the semantic-based regularization technique. The first approach relies on the idea that prune values are supposed to be provably unfeasible, so we discourage the network to make provably unfeasible assignments. The second approach discourages the provably infeasible assignment and encourages the remaining ones, and employs the binary cross-entropy as a cost function. The third approach is very similar to the second one, but we replace the binary cross-entropy with the mean squared error. So the overall loss function is the sum between the categorical cross-entropy and the regularization term, but since the propagators are incomplete, we may inject incorrect information. So we need to tune the lambda value to find a trade-off between learning the constraints from the complete knowledge and from the incomplete one. The evaluation of the neural network is performed starting from a partial assignment which has not been seen during the training. Then we extend it with the most likely assignment according to the output of the neural network. And then we check that this assignment is globally feasible. We also evaluate a random estimator, which can optionally rely on the propagation of some of the constraint to prune some infeasible values. And it chooses an assignment according to a uniform probability distribution among the still feasible ones. This allows to assess the impact of using the offline knowledge during the search, something that is possible in our control setup, but that is impossible in a real-world problem. Our empirical analysis is focused on three questions of scientific interest. First of all, we want to assess if knowledge injection at training time can improve the network ability to suggest global feasible assignment. Then we investigate the effect of adjusting the amount of the empirical knowledge in terms of number of training examples and number of available solutions. And finally, we evaluate the effect of the knowledge injection at training time when constraints can be treated as soft, and we measure the violation. Some details about the setup. We focus on 7x7, 10x10, and 12x12 PLS instances. We employ a simple feed-forward fully connected neural network. We assume to have 10,000 initial solutions, and we employ the simple forward checking constraint propagator, but the method we have developed can be extended to any kind of discrete propagators. We compare several approaches. First of all, the model agnostic neural network, which is also the baseline and referred to AGN. And then the regularization method, a neural network trained with the regularization methods previously described, referred to as negative, BCE for binary cross-entropy, MSE for mean square error. And finally, we also compare the trained neural network with a random estimator that can optionally rely on the propagation of the only row constraints or the full problem definition. We then produce the feasibility plots that report on the x-axis the number of field cells in the considered partial solution, on the y-axis the feasibility ratio. Methods that can rely on the propagation of the constraint during the search are highlighted using solid lines. And they are representative of the behavior of what can be achieved if we can exploit the symbolic knowledge, the constraints propagation during the search. First of all, we make a comparison of the regularization method for different values of lambda on the partial Latin square of size 12, which is the most challenging instance of the PLS among the one we have examined within this work. Here we show the results when all the constraints are propagated during training and during the search for some of the random estimators, for random estimator. And as we can see, the negative approach, which is the brown line, is hardly distinguishable from a simple random estimator that cannot rely on any constraint propagation, which is the orange line. This can be due to the fact that this regularization approach encourages the network to keep the output the lowest as possible instead of discouraging the network to make probably unfeasible assignments. For the MSE and BCE regularization approach, we need to find a lambda value that allow to find a trade-off between learning the constraints from the correct knowledge and from the incomplete one. So we are not directly interested in the global feasibility ratio, but on try to learn the constraint propagation. Here are the results when the only row constraints are propagated. Then we investigate the effect of the knowledge injection at training time for different problem dimensions. Here are the results for the propagation of the full problem constraints. And as we can see, as long as the problem size is small enough, a model agnostic neural networks perform better than any other approaches, which is the orange line. But with increasing of the problem dimension, the improvement gap narrows very quickly. In this case, the regularization, the knowledge injection at training time, which is represented by the MSE, the green line, and the BCE, which is the red line, does not provide any advantages. Then we measure the effect of reducing the training set size to the 10% of its initial size. And this is important because it has a strong impact on the ability of machine learning algorithms to learn and generalize. Here are the results when all the constraints are injected during the search are propagated. And as we can see, the model agnostic neural network, the orange line, and the BC approach, which is the red line, have a major drop in performance. Instead, the mean square error regularization approach, which is the green line, effectively learn the constraints propagation. Here are the same conclusion can be drawn when we propagate the only row constraint. Then we investigate the effect of knowledge injection in training time when a small solution pool is available. So we reduce it from 10,000 to 100. And we apply the deconstruction procedure multiple times for each solution to gather a training set of the same dimension of the original one. Here we consider the only mean square error regularization approach. We collect the result for the propagation of the full problem constraint and the only row constraint in a single plot. And again, we can draw the same conclusion as for the previous analysis. Knowledge injection at training time is allows to effectively learn the constraint propagation. And we have only a minor drop in performance when the problem size grows. And then finally, we consider a scenario in which we can treat the constraint as soft, and we are interested in measure their violation. This could be of interest, for example, for over-constraint problem. We start from an empty square and we generate 500 solutions, using the trained neural network to guide a depth-first search. We train two model agnostic neural networks on a training set obtained by the construction of 10,100 solutions, and the same for the regularization approach. As we can see from the table, which reports the number of constraints violation per generated solution, the knowledge injection at training time allowed to drastically reduce the number of constraint violation. The model agnostic neural networks performs better than a random estimator, but it has a major drop in performance when a very small solution pool is available. So to conclude, as long as enough empirical knowledge is available, then a pure data-driven approach performs better. But increasing the problem dimension, then the advantages provided by the data-driven approach narrows very quickly. And in this case, knowledge injection in training time is not helpful. Instead, when the empirical data are scarce, knowledge injection at training time has a dramatic effect and allows to effectively learn the constraint propagation that cannot be employed during the search. Finally, if we can treat the constraint in soft and we are interested in measuring their violation, then knowledge injection allowed to drastically reduce their violation. So thank you for your attention, and if you have any question, we are pleased to answer you.
Thank you very much for the talk, Mattia. Are there any questions? Are there any questions in Vienna?
At the moment, no.
Okay. So I have a few questions regarding the experiments. So one question is, how large are the training times?
Well, it depends on the hardware you have at disposal. I mean, we don't have measured the training time because it's very hardware specific. But all the generation of the training set generation, which is the most challenging part, is done offline. So since the neural network is not so big, the training time is not computationally expensive.
Okay. Another question has to do with so you consider the very specific problem, the Latin squares. Could the conclusions be different if you were to consider other generic problems, other different types of problems? So the question is, how do your conclusions generalize beyond Latin squares?
I definitely think that there is more experiment. We need to perform other experiments on other set different from the partiality square. Of course, I think they can generalize to other problems, but maybe we need to tune some value like the regularization, the scalar value we have used to tune the regularization term in the loss function. So I think that could be the most challenging extending this approach to other problems.
So if I may add something, so this was a really controlled experiment. Ideally, we should have considered at least two problems to see how well the results ported from one to the other. That's one shortcoming of the work, a limitation, and we are aware of that. We prefer to focus deeply on a single problem because it was particularly well suited to be studied. I think we don't know for sure whether we're going to generalize the results are stable to on other problems or not, but I think there is a good chance, and that's basically because the kind of trend observed here are something that are partially known also in other applications that try to inject a priori knowledge into neural network, other knowledge distillation approaches. So to say, and it sort of makes sense. So there is a good chance that some degree of generalization can be obtained.
Okay, thank you. Are there any more questions? Okay, so I will have another question. So in terms of the architecture of the neural network, did you consider different architectures or did you focus on a specific one? Do you understand my question?
Yes, we use a simple feed-forward neural network because we don't want to choose an architecture which is problem specific. So we want to be the general, the most general as possible.
Yeah, I understand that. Thank you very much. But it's not that what I'm asking. The question is, how many hidden layers? Did you try different hidden layers, different number of neurons per hidden layer?
No, we just try, yes, we try different architecture. The original work adopted a very deep neural network with residual blocks, but it achieves basically the same results. So I think the architecture we have chosen, which has a 3D layer, is more than enough to solve this kind of problem.
Okay, thank you very much. Are there any, we have time for one more quick question. if anyone has any more questions. If not, I would like to thank the speaker and Michele for answering the question.